Differential Equations, Lesson 2, Solving Differential Equations by Separating Variables. So we're going to have a look at a process which will allow us to solve differential equations. Let's start with a simple example, which is dy by dx equals y squared. Now, this is a little bit more complex than the examples we looked at previously. We can't just integrate this, because how do we integrate y squared with respect to x? So we're going to look at another process. Now, the first thing I'm going to do is divide both sides by y squared. This gives me 1 over y squared dy by dx is equal to 1. Now, the process that we're going to apply is something called separating variables, with the idea being that we collect x variables on one side and y variables on another side. Now, the next step that I'm going to write down isn't really proper maths. It's a shortcut that we write down, or sometimes write down. We don't have to include it. So imagine I have 1 over y squared dy, and I multiply both sides by the dx. Now, this is not a real piece of mathematics here, because of course dy by dx is a derivative. It is not a fraction. It is not some kind of division where we can multiply both sides by the denominator. So I have 1 over y squared dy equals 1 dx. Now, I'm going to put this in quotation marks because it isn't really a proper piece of mathematics until we get to the next step, which is where we integrate both sides. So if I write down the integral of 1 over y squared dy is equal to the integral of 1 with respect to x, now I have a proper piece of mathematics. Now, the part that I put in quotation marks, you won't get marked down in an exam for writing it down because it's a simplification. It's a way in which we can work that will allow us to try and get to the correct process eventually, but it's not a real piece of mathematics. The real mathematics would take place here, where I integrate both sides with respect to x. So if I write down the integral of 1 over y squared dy by dx with respect to x is equal to the integral of 1 with respect to x. This is the true mathematics that is happening on both sides. It's a little bit more complex, but it is the actual process. So of course the left-hand side simplifies to the integral of 1 over y squared dy, and the right-hand side is the integral of 1 dx. So we end up at the same point we got to here, but our notation is slightly more complex. So this is essentially the correct version of the mathematics. What you're seeing on the left-hand side in the quotation marks, it's a more simplified process. Once you get to the part that we've highlighted in green, that is absolutely correct, and we can proceed from there. So let's perform the integration. So on the left-hand side, we have the integral of 1 over y squared with respect to y. I'll rewrite that as y to the negative 2. On the right-hand side, we simply have the integral of 1. So this gives us negative y to the negative 1 equals x plus c. Now, you do not need to include a constant on both sides. You can just put the constant in one place, because in theory, if there were a constant on both sides, we could just combine the constants as 1 on one of the two sides. So just pick a side on which to put the constant. It doesn't actually matter. Now, from here, we might be asked to find a general solution, so rearrange this to the format y equals. So I can do that. Y equals negative 1 over x plus c. And I have a general solution. Now, if I want to find a more specific solution, I need to be given some boundary conditions. I need to be given some information that I can use. So I might, for instance, be told that if x equals 0, y is equal to 2. This allows me to substitute into my general solution. So 2 equals negative 1 over c, which gives me c equals negative a half. This means I can rewrite my solution as negative 1 over x minus a half. Now, that's a little bit messy. You're sometimes asked to present answers in a particular way. I'm going to multiply the numerator and the denominator of this result by negative 2, which gives me y equals 2 over 1 subtract 2x, and there is my final answer. So let's have a look at a second example. We're going to solve the differential equation dy by dx equals xy, and we've been given some boundary conditions that we can use later on. So again, imagine we are going to collect y terms on the left and x terms on the right. So that would give us 1 over y dy equals x dx. Again, this is a somewhat illegal piece of mathematics here. I'm going to make it fully legal by putting in the integral signs, and then we are absolutely fine. Let's integrate the left-hand side here. That gives me ln of mod y equals a half x squared, and I'm going to put the constant on the right-hand side here. Now, if we're given some further information, we may not necessarily need to include the modulus sign. So for instance, if I'm told in the question that y is greater than 0, that allows us to lose the modulus sign, so I can simplify to ln y equals a half x squared plus c. If we're not given that information, we need to leave that in place. Now, this is the general solution, but quite often we are required to format it in a particular way. So I would like to write this in the format y equals, making y the subject, so I'm simply going to take e to the power of both sides. So I have y equals e to the power of a half x squared plus c. Now, what you will see in many differential equation questions is that there are simpler ways of writing answers like this. So let's have a look at what I could do with this. I'm going to split up the right hand side, so it's y equals e to the half x squared multiplied by e to the c. Because of course, when we multiply terms and they have the same base, we can add the indices. I've just used that rule backwards. Now, e to the c is a constant. There's nothing particularly special about it having an exponential involved as well. It is just a constant. So what I'm going to do is I'm going to say let e to the c equal a, which is just another constant. And it's a slightly simpler way of writing e to the c. This gives me y equals a multiplied by a half x squared, where we've replaced e to the c by a. So I now have a simpler form of my general solution. We were given some boundary conditions over here. Let's substitute them in. So y equals 5 when x equals 0. Now when x equals 0, e to the 0 is obviously just 1, so a is equal to 5. And this then gives me y equals 5 e to the half x squared as my answer to this question. Let's have a look at another example. dy by dx is equal to 4 cos 2x. So there are no terms on the right hand side containing a y, so my separation of variables is going to look like this. And again, to make sure I've got legal maths here, let's put in the integral signs and integrate both sides. We can write a 1 here as well if it helps with the integration. So on the left-hand side, this integrates to y. On the right-hand side, we have 4 cos 2x, which is going to integrate to 4 over 2 sine 2x plus a constant. So this gives me y equals 2 sine 2x plus a constant. I don't have any boundary conditions here, so I will have to leave the result as a general solution. Example 4, we're going to solve the differential equation v dv by dx plus 4x equals 0. So differential equations don't just have to be in terms of y and x, other variables are available as well. Now, we're going to need to do a little bit of rearranging here first of all. And I've chosen this example because it's not always obvious to people that you have to do this step here first of all. So subtract 4x. Now let's separate the variables. So we have this, and let's integrate both sides like this. So we've separated the variables, now let's integrate. So on the left hand side we have a half v squared, and on the right hand side we have negative 2x squared plus c. Now we might be expected to write this in terms of v, so we might be expected to change the subject to v. So let's multiply through by 2, so we have v squared equals negative 4x squared. Now I could write plus 2c here at this point, but if c is just a constant, 2c is just another constant, so I'm just going to write c again as it doesn't really make any difference here. There may be questions where we have to be a little bit more careful if we're required to show that an answer has a particular format, but I'm not required to do that. We will look at many more examples like that a little bit later on. So v then equals the square root of c minus 4x squared. If you really wanted to, you could include 2c if it's worrying you that we haven't written the constant being multiplied by 2, but genuinely it doesn't actually matter. We can just write it as a single constant. Now I've chosen example 5 because it's one in which I've seen many errors previously. I've seen people try to add h to both sides and then get very stuck when they try to separate the variables. You have to treat the right hand side, 20 take away h, as a single entity in order to be able to do this. So let's divide both sides by 20 take away h. So on the left hand side we have 10 over 20 take away h, and on the right hand side we simply have this. Again, you can write a 1 in if it helps with the integration. Let's put in our integral signs. The factor of 10 could belong on either side, it doesn't really make any difference. Now we can see we have an integral on the left hand side that's going to result in a ln, or a natural log answer. So this will give us negative 10 ln mod 20 take away h, and on the right hand side we simply have t plus a constant. Now this is the answer we get when we integrate. We might be expected to write this in a particular format. We might be expected to rearrange it so that it's in the form h equals. Now to do that, I then have to divide both sides by negative 10 first of all. So we have ln of 20 take away h equals negative t over 10 plus a constant. And again, it's just a constant. It doesn't matter. There's no real value here in this particular question of writing it as constant divided by negative 10 or negative 1/10 of a constant, because that is simply just still another constant. So we now need to take e to the power of both sides. So this leaves me with 20 minus h on the left hand side, and then e to the negative t over 10 plus a constant. And you've seen this previously. We can split up the right hand side, e to the negative 10 over t multiplied by e to the c, and I'm going to say let e to the c equal a, another constant. So 20 take away h equals a e to the negative t over 10, which then gives me h equals 20 minus a e to the negative t over 10. And of course, we can't find a unless we have further information. Now, if you're worrying about which format to leave your answer in an exam situation, you will always be given a little bit more guidance, because it makes sense to try and direct students to write an answer in a particular format. If nothing else, it makes the marking a little bit easier. Now, if you're just solving a differential equation for the fun of solving a differential equation, well, then it's up to you as to how you present your final answer, unless you're specifically told in a question to provide a particular format. You're going to have a go at the following questions. The answers will come up on the next slide, so do pause, have a look at the questions and see if you can solve each of these differential equations by separating the variables. So let's have a look at the answers to the questions that we have set. So the first one, dv by dt equals 10e to the negative a half t. Let's separate variables, so dv equals 10e to the negative a half t dt, and I'm going to quickly add in my integral sign so that this then becomes a proper piece of mathematics. Let's now integrate, which gives me v equals negative 20e to the negative a half t plus c. Question 2. We have dy by dx equals 3x squared y. So separating variables, we have this. And let's integrate as follows. This then gives us ln mod y equals x cubed plus c, and I can do a last step of rearrangement, y equals e to the x cubed plus c. Now this is one of these questions where you're quite often asked to then split up the exponential like this and then rewrite in this format here where we've let a equal e to the c. Question 3. So separating variables, we have integral dx equals the integral 3e t to the 2t plus a 2. I've included the integration step as well as the separation of variables all in one step of working here. So we have x equals 3 over 2e to the 2t plus 2t plus c. So question 4, we go straight to this, integrating both sides. So we have ln mod y equals ln mod x plus a constant. Let's take e to the power of both sides. So we have y equals e to the ln mod x plus c. Now this is interesting because if we split this up like so, e to the ln of x is of course x. So this gives us y equals x e to the c, or y equals ax, where a is the constant equal to e to the c. Question 5. We have 1 over e to the y take away 3 equals x to the negative half on the right hand side, and we'll take the integral of both sides like that as well. Now on the left hand side we're going to rearrange this so it's e to the 3 subtract y, integral of. On the right hand side we simply still have x to the negative a half dx. Now integrating both sides, I'll do the working up over here, that gives us negative e to the 3 take away y equals 2x to the power of a half plus c. Now you might be asked to rearrange this for y, you might be asked to rearrange this for x. There are various different routes we could take with this. Let's imagine we have to write this in the format y equals. So we'll multiply both sides by negative 1, which gives me e to the 3 minus y equals a constant, take away x, 2x to the power of a half. And again, the constant we're using is just the negative of the previous constant, but for simplicity I'm going to write it like this. Then take natural logs of both sides, so ln mod c minus 2x to the half on the right hand side, and this then simplifies to y equals 3 subtract ln of mod constant take away 2x to the power of a half. Now question 6, to finish off, this when we separate variables gives us the integral of 1 with respect to y equals the integral of 1 over 2 minus x with respect to x. So the left hand side simplifies to y and, well, integrates to y, and the right hand side integrates to negative ln mod 2 minus x plus c. And we have finished.